hello everyone. I'm Max. I work in the Microsoft Offensive Research and Security Engineering team. And I'm going to talk about a security review we did of TDX, which is a new confidential computing technology from Intel. So it's a review we did a year ago in partnership with Intel, and so I'm going to talk about what TDX is, how it works, how we approached it from a security point of view, and then going to present two vulnerabilities we discovered in it before concluding with a few takeaways. So in a standard virtualization architecture, you have a hypervisor that runs guests. The hypervisor is typically owned by a cloud provider, and the guests are typically cloud customers. In this architecture, there is, by definition, no confidentiality guarantees provided to the guest because the hypervisor has access to the guest's memory and to the guest's registers, and so it can see all of the guest's data. That's, of course, a problem if the cloud provider gets compromised, because if an attacker takes control of the hypervisor, then it's easy for them to exfiltrate all of the customer data. So in order to fix that problem, there needs to be a change in architecture. There needs to be a new architecture. And on Intel, that architecture is called TDX. So TDX stands for Trust Domain Extensions. And the idea is that the hypervisor does not longer run the guest directly. Instead, it talks to a new piece of firmware called the TDX module. And it's the TDX module that runs the guests in an isolated way. So the TDX module in green here is the core component of the TDX architecture. And it acts as a bit of a gatekeeper to ensure that the guest memory is encrypted and that the guest registers are not exposed to the hypervisor. And so in this new architecture, if the cloud provider gets compromised, then it's not possible to steal the customer data because it's protected by TDX. So TDX provides confidentiality and integrity guarantees. It will be available in future generation CPUs by Intel. So it's about to become available in the market, but it isn't yet completely. And at Microsoft, we are very interested in strengthening the security promises that we make to our customers in our Azure cloud. And so we're very interested in the TDX architecture, and that's why we performed a security review of TDX to learn more about how it works and see whether the security promises of TDX truly hold. So let's dig into the technical details of how the TDX module works. So the TDX module is, first of all, a purely software component. It doesn't run on a separate chip on a specific hardware. It runs on the main CPU in the system. It is actually open source, so you can download its source code from the Intel website. It is programmed in C, compiled by Clang, and results in an ELF binary. It uses the standard x64 instruction set, so no magic instructions or anything like that. And it runs in ring 0 64-bit page mode, which is similar to a traditional kernel. At initialization time, the TDX module is loaded in a range of protected physical memory called the SIM range. And by protected, I mean that the hypervisor does not have access to it. Only the TDX module can write into the SIM range. Once TDX has initialized, the TDX module executes only when it is explicitly invoked. And to do so, there are two new instructions introduced in the CPU, SIMCALL and SIMRET. So it's a call-read couple that allows to jump in and out of the TDX module. So the hypervisor can execute the SIMCALL instruction. That will cause the CPU to jump into the TDX module. And then when the TDX module executes SIMRET, the CPU jumps back to the hypervisor. In terms of privileges, the TDX module runs in a privilege mode that is similar to the normal mode. It just has access to the SIM range in addition. So if you represent as a timeline, you first have the hypervisor running in host mode, in standard mode. When it executes the SIMCALL instruction, the CPU jumps into the TDX module and switches to the TDX mode. And here, the SIM range becomes accessible, so the protected range in physical memory becomes accessible. And when the TDX module executes SIMRET, the CPU jumps back to the hypervisor, switches back to host mode, and here, the SIM range becomes not accessible anymore. The SIMCALL instruction that allows to jump into the TDX module is actually used to implement an interface that resembles syscalls on traditional kernels. So before executing the SIMCALL instruction, the hypervisor can set a specific value in array X to select a command. Then it populates the rest of the registers with some parameters. When it executes SIMCALL, the CPU jumps into the TDX module. And here, the TDX module dispatches the command selected in array X using the parameters supplied in the rest of the registers. So it's pretty much similar to the syscall interface on normal kernels. It's just called SIMCALL here, but it's the same principle. There are around 80 commands implemented in the TDX module, so 80 syscalls if you want, most of which have to do with guest management. So there's a command to create a guest, there's a command to assign memory to a guest, for example, and so on. And eventually there's a command to run a guest. That last command, run the guest, is where the guest runs for real on the CPU. So if we represent as a timeline, you first have the hypervisor executing in host mode. It executes the simple instruction to invoke the command run the guest in the TDX module. So the CPU jumps into the TDX module. The TDX module dispatches the command and then performs a VM launch. And that's where the CPU jumps into the guest and starts running the guest for real. So the guest executes. At some point, the VM exit occurs. So the CPU jumps back to the TDX module. And then the TDX module, in turn, executes simret. So the CPU jumps back to the hypervisor. That's the full workflow of how guests are run in the new TDX architecture. So now that we have presented the basics of the TDX module, there are two questions that arise when we look at it from a security point of view. The first is, where do we actually look for vulnerabilities in this new architecture? So there are two natural attack surfaces that I highlighted in red here, the hypervisor to TDX module and the guest to TDX module. These are two security boundaries that the TDX module has to protect. And in this talk, I'm going to talk about only the hypervisor to TDX one. And the attack scenario is the one that I mentioned earlier, which is that if the hypervisor gets compromised, then does TDX truly protect the customer data here? So that's the attack scenario we're going to keep in mind here. Then the second question that arises when we look at TDX from a security point of view is, how do we actually execute the TDX module if we want to exercise it or to fuzz it, typically? So to execute the TDX module, you have to have a new physical machine that has the latest Intel generation CPUs that supports TDX. Right now, that means a future machine because they're not available on the market yet. Once you have that setup, you have to have a setup where you execute the simcall instruction to try to invoke commands in the TDX module to try to fuzz it, for example. The problem is that in that environment, you can't attach a debugger to the TDX module, so you can't debug it. You don't have access to the register states and to the memory. And so your life is very difficult if you try to execute the TDX module for real. With that in mind, we started developing at Microsoft a quick tool that we called Cornelius that was initially just a toy, but it turned it into a full emulation framework that allows to run the TDX module, so the firmware, as a VM without having TDX hardware. In that environment, we have full introspection capabilities, of course, because we control the VM in which the firmware runs, so we have access to the memory and to the registers. And we even went the extra mile of developing support for sanitizers on the TDX module. Specifically, we support ASAN, UBSAN, and SANCOV, assisted by our Cornelius emulator. So with Cornelius, we basically went from having a very difficult life with physical machines to having a very easy life now, because we're now able to run the TDX module in a VM without having TDX hardware, and with full introspection capabilities and sanitizers. So it's a perfect environment to do security research. I had a quick demo to showcase how it works. Not much to see. It's just a demonstrator that we wrote that executes several commands in the TDX module, and they all execute successfully, that's all. If we zoom in at the end, I said that we support sanitizers, and specifically we support SANCOV, the coverage sanitizer. So if we zoom in at the end, Cornelius dumps the coverage count, and in this case, there were 4 CPUs on which the TDX module ran in the VM, and we executed most commands on CPU number 0, and so that's why it has a higher coverage count, which makes sense. So anyway, it's just to demonstrate that it works. I'll come back to Cornelius in an instant. So now that we know which attack surface to look for, and now that we have our execution environment to fuzz the TDX module, we started looking for vulnerabilities in the TDX module, and we realized early on that we're not going to find easy vulnerabilities because there are overall good programming guidelines in the source code. So Intel performs extensive testing, and they also use static analysis, which catches the vast majority of the bugs at the source code level. Then at the binary level, the TDX module also has good mitigations. So it has ROP to prevent, it has shadow stack, sorry, to prevent ROP. It has IBT to prevent COP. It has ASLR, proper permissions on the pages, the stack cookies, of course, and so on. So overall, it's a good code quality for a firmware, much better than usual. And so we realized that we're going to have to think harder than just looking for off-by-ones in the source code. So instead, we started looking at more architectural and logical types of bugs, and specifically at the context switching logic that takes place in the TDX architecture. So during the sim calls and simrets to jump in and out of the TDX module, the CPU has to perform a context switch. It means that it has to copy the values that are contained in the CPU registers into memory, so it saves them to memory. And then it installs new values from memory into the CPU. So if we represent here and say that there's an Intel CPU with 6 registers, during the sim call, what happens is that the values initially of the registers are the hypervisor values. The CPU saves them to memory. And then it installs the values of the TDX module into the CPU so that the CPU can then start executing with a safe set of initial registers. So that's how the CPU goes from having hypervisor values before the sim call to having TDX module values after the sim call in the registers. Now, the CPU does not actually context switch all of the registers. Some of them need to be context switched manually by the TDX module itself in software. And that naturally raises the question of, does it do so correctly? So we made a quick experiment. We knew that the XMM registers are switched neither by the CPU nor by the TDX module. And the reason for that is that the TDX module doesn't use the XMM registers, so it doesn't bother context switching them. So it means that the values persist. When the hypervisor sets its own values in the XMM registers, they're not context switched. So after the sim call, the values are still there, and the TDX module executes with still the hypervisor values loaded in the CPU. And that's because the TDX module doesn't use them. So with that observation, we thought that, well, since the TDX module doesn't use XMM, then we can disable XMM in Cornelius, right? There shouldn't be a problem since the TDX module doesn't use these registers. So we made the change in Cornelius, and we rerun the demonstrator that I showed you earlier. And as soon as we run it, we see that, in fact, the TDX module crashes in the VM. And the reason for that is that the TDX module does actually use the XMM registers, but forgets to context switch them during the sim calls and the simrets. And that's a bug that could be a vulnerability. So if we show the full workflow, what happens is that during the sim calls, the values in the CPU persist. So they're not context switched, and the TDX module executes with the values still loaded. At some point, the TDX module is going to overwrite XMM0, for example, with a new value that it has. And then when it executes simret, the value persists again because there is no context switch, and so the value goes back to the hypervisor. So there are two impacts in this bug. The first impact is that whatever value the hypervisor initially had in XMM0 before the sim call actually gets corrupted by the TDX module after the sim call. So if the hypervisor had typically stored a pointer in that register and then tries to dereference that pointer, then there could be memory corruption in the hypervisor. So that's the first impact, state corruption, possible state corruption in the hypervisor. And then the second impact, which is more interesting for us, is that whatever value the TDX module wrote in XMM0 actually persisted during the simret and actually therefore leaked to the hypervisor. And so if the TDX module had actually stored a guest secret in the XMM0 register, then that secret leaks back to the hypervisor during the simret. And so that's the second impact, possible information disclosure. So two impacts for that bug. We realized after more investigation that the second impact was not happening in practice, because in practice, the TDX module does not store guest secrets in the XMM registers. So even though the XMM registers leak back to the hypervisor, they don't contain secrets that are worth bothering with. So Intel fixed the bug as a functional bug and not as a security bug because it was not an information disclosure technically, which makes sense. But it's a bug we found in only 20 seconds. 10 seconds to get the idea of disabling XMM, and then 10 seconds to rerun Cornelius without XMM and see that the TDX module crashes. So 20 seconds to find a bug that could have been potentially critical if the second impact had materialized. So that's a very good return on investment. And so we started digging deeper into the context switching logic in the hope of finding more bugs. So we did find increasingly more interesting bugs which were on the verge of being security issues, but not quite, until we arrived at a first critical vulnerability, which was in the context switching of the processor trace registers. So processor trace is a tracing feature implemented in the CPU, and the principle is that the CPU records the execution of your software and creates a log in memory that summarizes what your software did. The TDX module supports processor trace in guests so that the guests can enable processor trace on themselves when they run in the TDX architecture. Processor trace is controlled by several registers, two of which are important here. The first is the control register that has a trace enable bit, and that's the main toggle to enable or disable processor trace. That's the trace enable bit. Then the second register is the output base register. It contains the physical address at which the CPU is going to write the log in memory. So typically, if you want to enable processor trace, you first set the address of a physical page in output base, then you set trace enable to 1, and from then on, the CPU starts logging the execution of your software and creates a log in memory at the address that you designated in the output base register. So if we look at the context switching that takes place for these two processor trace registers, there's actually two context switches. The first is during the SIM calls. The CPU doesn't perform a full context switch. It just forces the value of trace enable to 0. It means it basically force disables processor trace during the SIM call. Then when the TDX module performs a VM launch into a guest, this time a full context switch takes place to install the values of the guest into the CPU so that the guest can run with the values it wants. So the hypervisor has its own values on the left, the guest has its own values on the right, and the TDX module in the middle is in an intermediary state where processor trace is just force disabled. Now, if you focus on the second context switch on the right side, the VM launch one, that's, as I said, a full context switch. So the guest values are in memory, they are copied into the CPU, and then the CPU is ready to start running the guest. So if we represent, so that's a context switch that is made not by the CPU, but by the TDX module itself in software. So if we represent as a timeline, you first have the guest executing, the TDX module executing. So it's processing the command run the guest. As part of processing that command, it performs the context switch here to install the two registers from memory into the CPU, so it copies them into the CPU. And then at some point later, it performs the VM launch, which is where the guest starts running. Now, what's noticeable here is that there is actually a time window between the context switch and the VM launch. When the context switch is finished, the TDX module is actually still executing. The CPU hasn't yet jumped into the guest. So that could create a theoretical problem because what if the trace enable bit on the right side in the in-memory state is set to 1? If the trace enable bit is set to 1 in memory, then when it gets copied into the CPU, it's also set to 1 in the CPU. And that means that processor trace gets enabled while the TDX module still executes after the context switch and before the VM launch. So that could be a theoretical problem where processor trace could be enabled in the TDX module itself. Now, in practice, it's not supposed to be the case because due to a complex set of interactions, there is basically the guarantee that the in-memory state, the in-memory value of the trace enable bit is always 0. And so when the context switch occurs, the value 0 gets copied into the CPU, and therefore it's still 0 in the CPU, and therefore processor trace does not get enabled after the context switch immediately. So that's an assumption that is correct to make and that we verified and that holds overall, except in one specific case, which is on debuggable guests. So debuggable guests are a specific type of guest, and it's a type of guest for which the in-memory state on the right side is actually accessible to the hypervisor. And the hypervisor can write whatever values it wants into the in-memory state on the right side. That means that the assumption that the in-memory value of the trace-enabled bit, the assumption that this value is 0 is actually wrong because the hypervisor could have set it to 1 on a debuggable guess. And if that happens, it means that the hypervisor can therefore enable processor trace in the TDX module because the value 1 then gets copied into the CPU, and from then on, processor trace gets enabled in the TDX module. So if we summarize as a timeline, you first have the TDX module that executes, performs the context switch to copy the processor trace registers from memory into the CPU. But here, it could have been a debuggable guess on which the hypervisor set trace enabled to 1. And so it means that as soon as the context switch is finished, processor trace gets enabled right away. And therefore, the TDX module keeps executing with processor trace enabled before it jumps into the guest. So there's a window here, a time window, during which the TDX module executes with processor trace. And that's a window of opportunity for us, the attackers. So if we assemble the different pieces together, I said that on debuggable guests, the hypervisor has access to the in-memory state. So it can control the output base register and the trace-enabled register. That means it can control the output base, actually. And therefore, the hypervisor can decide where in memory the log gets written to, the log that the CPU is going to create. So that's number one. Number two, there are actually additional processor trace registers that exist that I didn't mention, but they allow to control what kind of data the CPU is going to write into the log. And given that the hypervisor has access to the in-memory state, it can control the value of these registers, and therefore it can control what data the CPU is going to write into the log. The log, which is created at the output base, at the output base address that the hypervisor also controls. So that's number two. And then number three, I said earlier that the TDX module executes in TDX mode. And in that mode, the SIM range is actually accessible, the protected range in physical memory. So that's number three. If we assemble the different pieces together, we can see that, in fact, the hypervisor can set the output base register to point into the SIM range. And by then enabling processor trace into the TDX module, it can cause the CPU to override the TDX memory with the processor trace log. The log, like the contents of which, are also controlled by the hypervisor. So it means that the hypervisor effectively has a write-what-where primitive into the TDX memory. And therefore, it can achieve full privilege escalation because it can overwrite the instruction bytes of the TDX module and inject its own shellcode and its own backdoor. Now, what about ASLR? I mentioned earlier that the TDX module has good mitigations, and among other things, it has ASLR. Well, in this case, it doesn't really apply because ASLR is only applied on the virtual memory, not the physical memory. And here, with our primitive, we are actually overriding the physical memory, which is not subject to ASLR and is not randomized. In other words, the hypervisor knows exactly where the TDX module is in memory and knows exactly where to override it, where to overwrite its instruction bytes because there is no ASLR. So ASLR is essentially useless in this vulnerability. So if we summarize the attack scenario, if you have a cloud system that's running with TDX, you have a target customer here that you would like to attack. So an attacker compromises the cloud provider, takes control of the hypervisor. First step, create a debuggable guest. So that's just going to be a dummy guest that is just debuggable for the purpose of exploiting the vulnerability. Then next step, exploit the vulnerability to escalate privileges into the TDX module via the debuggable guest by enabling processor trace and overriding the memory of the TDX module. And then number three, once the attacker controls the TDX module, then it's trivial to exfiltrate the customer data. And so with this vulnerability, we achieve a full defeat of the confidentiality promises made by TDX. So Intel assigned the following CVE to the vulnerability. It's a vulnerability that affected all the versions of the TDX module, and Intel fixed the latest version. So that's the first vulnerability I wanted to present, and it shows how we can defeat the confidentiality guarantees in the new TDX architecture that is supposed to provide these guarantees. There is then a second vulnerability which we found still in the context switching logic, but this time not in the TDX module, but in the CPU itself. So I've been talking about the SIM call instruction and how it's used to implement an interface to jump into the TDX module and invoke commands and so on. Now, if we forget about the TDX module completely and focus only on the very simple instruction itself, if we look at the pseudocode provided in the Intel specification, there's something that is striking. There's two things that are striking at the beginning. The first thing is that the SIM call instruction is actually unconditionally recognized by the CPU. It means that there is no toggle to enable or disable it. It's just that if the CPU supports TDX, then it's going to unconditionally recognize the instruction, and anybody can execute it in the system. That's weird because normally, when a new CPU feature is introduced, there's supposed to be a toggle to explicitly enable it before using it. It's not supposed to be enabled by default unconditionally. So that's unusual, but not a security problem at a first sight. The second thing that is striking in a pseudocode is that the SIM call instruction has a VM exit reason associated to it. And so if we forget about the whole TDX architecture and come back to the previous model where the hypervisor directly runs the guest, in that model, if the guest executes a privileged instruction, the CPU performs a VM exit, so it jumps back to the hypervisor, and it tells the hypervisor, hey, the guest just tried to execute that instruction, please emulate it. So SIM call has a VM exit reason associated to it, and that means that if the guest executes the SIM call instruction, then the CPU triggers a VM exit, jumps to the hypervisor, and tells the hypervisor, hey, the guest just execute the SIM call instruction, please emulate it. That's also weird and unusual because normally there should be a toggle here to enable the VM exit also. The VM exit is not supposed to be unconditionally raised by the hardware, by the CPU. So that's weird again, but still not a security problem at a first sight. Now, if we think more about TDX, I said that it's a new feature, right? So it's going to be available on future CPUs. But the current hypervisors that exist on the market currently, like Hyper-V and Linux KVM, they don't know about TDX, and they don't know about the SIM call instruction either. So what would happen if a guest executes the SIM call instruction, but the hypervisor does not actually know about TDX and doesn't know about the SIM call instruction, and therefore doesn't recognize the SIM call VM exit? Well, what happens in that case is that the hypervisor kills the guest, because if it doesn't know how to emulate the operation, the default behavior is just to kill the guest. So that's interesting, but still not a security problem at this point because it's only a self-denial of service. If the guest executes the SIM call instruction and the hypervisor doesn't recognize it, then the hypervisor kills the guest. So it's just a self-denial of service from the guest point of view. So still not a security problem. Now, things get spicy when we think about nested virtualization. In a nested scenario, you have a hypervisor that runs a guest that is itself another hypervisor that runs another guest inside of it. In that scenario, if the nested guest down here executes the SIM call instruction, the CPU raises a VM exit to the outer hypervisor, the one at the top. And if the outer hypervisor doesn't recognize the SIM call VM exit, then it kills the whole guest, which means it kills both the guest hypervisor and all of the nested guests underneath it. So that's more interesting. We do, at Microsoft in Azure, just like other cloud providers, we do use nested virtualization in certain scenarios, such as containers. So if you book a container on Azure, you're going to have access to a nested guest here, guest number 4, for example, and the rest of the guests nearby are going to be other customers in the system. So you can maybe sense now where the problem is for us with the SIM call instruction. It's that if a malicious customer, guest number 6, for example, executes the SIM call instruction, that generates a VM exit to the outer hypervisor. But if the hypervisor doesn't recognize the SIM call instruction, then the hypervisor kills the whole guest, which means it also kills all the other guests of the other customers in the system. So essentially, because of the fact that the SIM call instruction is unconditionally recognized, we can have the case where a malicious customer, guest number 6 here, can do a denial of service on a whole bunch of other customers in the cloud by just executing the SIM call instruction. What's more, there's actually a second bug if we look at the rest of the pseudocode of the SymCall instruction. There is a priority inversion. So the SymCall instruction is supposed to be executable only from kernel mode, not from user mode. The problem is that in that pseudocode, there is a priority inversion. The privilege check takes place after the VM exit. So the VM exit occurs before. And so if the guest executes SymCall in user mode, then the VM exit occurs, and the privilege check in practice never takes place. And so it means that in the previous vulnerability, when the malicious customers execute the SymCall, it doesn't even have to be in kernel mode to execute the SymCall instruction. It can directly execute it from user mode, and that's going to work. That's going to raise the VM exit. That is going to lead the hypervisor to kill the whole guest. So that makes that second mistake in the specification makes the first vulnerability even easier to exploit. So in terms of affected systems, we're talking about the case where the hypervisor doesn't know about TDX, doesn't recognize the SymCall VM exits. So that's a case that would typically be a future setup where you have an old hypervisor running on new Intel TDX hardware. And it's the combination of old hypervisor, new hardware that creates the denial of service condition here because of the fact that the new hardware raises a VM exit that the old software doesn't recognize. That's a setup that actually exists a lot in the cloud for various reasons, having an old hypervisor on new hardware. Specifically, when we migrate existing systems, existing software on new hardware, we can end up in the situation with old hypervisor and new hardware that would have led to a denial of service here. So Intel, denial of service vulnerability. So Intel assigned the following CVE to the vulnerability, and they issued a microcode update to fix half of the problem. So the microcode update fixes the priority inversion to make sure that the privilege check takes place before the VM exit. But they didn't fix the bigger issue, which is that the SymCall instruction is just unconditionally recognized by the hardware, and the VM exit can unconditionally occur too. So they're not going to fix it in hardware, and instead, you have to apply a software fix. So basically, the hypervisors have to be updated to just recognize the SymCall VM exit and not kill the guests in such case. So that's a change we actually made preemptively at Microsoft in Hyper-V a year ago. We made a change in Hyper-V for it to just recognize the SymCall VM exit and not kill the guests. And we pushed the change via Windows Update like 6 months ago. So if you've been running Windows, you already have the fix to prevent the denial of service. But now, the other hypervisors will also have to be updated. So Linux KVM, for example, also has to be updated to recognize the SymCall VM exit and not kill the guest. Otherwise, we're going to get denial of service conditions. So that's all for the two vulnerabilities I wanted to present, and that's how the whole TDX architecture works and the security guarantees that it has. We have now published a white paper that is a partnership between Microsoft and Intel, and it summarizes our security research, our findings, our methodology. We had overall 21 findings, 6 of which were confirmed vulnerabilities. So I talked about 2 here, but there's 4 more. My colleagues at Blue Hat Israel, at Microsoft Israel, made a talk at Blue Hat a few months ago to present 2 other vulnerabilities. So here's the YouTube link. And Intel has also now published a blog post that summarizes the partnership between Microsoft and Intel on the TDX technology and on the security of confidential computing in the future. The Cornelius framework that we developed that allows to run the TDX module as a VM is also open source now, so we published it on the Microsoft GitHub. If you're interested, feel free to have a look, if you have any feedback or want to contribute also. As I said, it's a great tool. It makes it very easy to do security evaluation of the TDX module because you don't even need to have TDX hardware. You can directly run it as a VM with sanitizers, with full introspection capabilities, so very easy to do security research. Overall, the TDX module and the whole TDX architecture actually is a very interesting target to look at. As I said, the TDX module is open source, so it's easy to review it for security vulnerabilities. It was written with security in mind, and finding bugs in it is hard at the source code level. And then at the binary level, it also has good mitigations, as I said. So the combination of all of that makes it a very good intellectual exercise if you are a security researcher and want to have a look at a new target. Finally, Intel has a bug bounty program that does cover the TDX module. And so it means that you can typically write your own fuzzer based on Cornelius that we have now open sourced. You can find bugs with it, report them, sell them, and get money out of it. So TDX is also a good business opportunity for us security researchers, in addition to being a good intellectual exercise. That's all. Thanks.